Lesson 8.4 deals with using exponential functions. First, we're going to take a quick look at a review of the graphs of exponential functions. We just want to match the function to its graph. We have 4 to the x, negative 4 to the x, and 1/4 to the x. Well, this first one is an exponential growth function because 4 is greater than 1, so we know it should go through the point 0, 1 and go up from left to right. It should be increasing. So this one goes through 0, 1, this one goes through 0, 1, but we want this one to be increasing, and so this is graph C. Our next one, which is negative 4 to the x, would take this function here and flip it over the x-axis because a negative out front flips something over the x-axis. And so if we flipped our C function over the x-axis, it would look like this one over here in A. So this is graph A. Obviously, this one then would have to be graph B, but why is that way? Well, we have a 1/4 as our base. That indicates exponential decay, so it should come down left to right. It should still go through 0, 1, and it will have an asymptote here along the positive part of the x-axis. What we want to do here is we want to look at exponential functions and see some uses. So as we get into that, we first have to be able to write exponential functions given certain information. So notice if 2 points of an exponential function of the form y equals a times b to the x, notice this doesn't have anything added in the exponent or outside the function. So it wouldn't necessarily work for that. But if you know 2 points, you can know the function or the function rule. So here's an example of how we can do that. Write the exponential function of the form y equals a times b to the x, whose graph passes through 212 and 596. Well, we know that it's in the form y equals a times b to the x. And what we can do here, this goes through this point, the x value is 2 and the y value is 12. So we can put that in here. The x value is 2 and the y value is 12. And we can do that a second time for this point. The x value is 2, so we plug that in for 5, and the y value is 96. As we can, maybe the easiest way would be to solve one of these equations for a, and then plug it into the other one. So I'm going to go ahead and solve this one for a, and we could do that by dividing both sides by b squared. And so a is equal to 12 over b squared. And now we can substitute. We can substitute this into the other equation. So we have 96 equals a, but we just here see that a is 12 over b squared. So that's our a times b to the 5th. Well, b squared, 2 of these will cancel with 2 of the b's here because this is like over 1. So we're down, cancel with 2 of them, so we're down to b cubed. So really what we have here is 96 equals 12b cubed. Dividing both sides by 12. 96 divided by 12 is 8 equals b cubed. Taking the cubed root of both sides, we get b is 2. So our b value is 2. All we need to do is find the a value now. We want it in this form. We just found b. Now we need to find a, so we can plug it back into one of these originals. In fact, this one's going to be the easiest one to plug it into. So we have a equals 12 over b squared. Well, we know b is 2, so 2 squared. 2 squared is 4. 12 divided by 4 is 3. And so, given these 2 points, we know that the exponential function is y equals a, which is 3, times b, which we found to be 2, to the x power. And there's the function that those 2 values fit. We'll need to use that fact later on as having 2 points to graph or to find equations of functions. So modeling exponential growth and decay, this is the main part is modeling, figuring out some things with exponential functions. So functions of the form f of x equals a times 1 plus r to the x can model both exponential growth, where r is greater than 0, and exponential decay, where r is between -1 and 0, of an initial amount a, so our initial amount we're calling a, constant percent change r, so this r up here actually has to do with a percent change, so a percent increase or a percent decrease, and a time period x. The base of the exponent 1 plus r is known as, or is called, the growth factor. And so it could be growing by that factor, or it actually could be losing value if it's exponential decay. So here's an example where we will get to use this. Beginning with a population of approximately 2 million people, Nevada was the fastest growing state from 2000 to 2010 with an average annual increase of 3.2%. Write an exponential function modeling Nevada's population growth in millions. So we're not going to write out 2 million every time, we'll just use 2. We just have to realize that our numbers are dealing with millions. So what we want to do here is we want to write a function. So f of x is equal to a times 1 plus r to the x power. Oops. And we'll plug in some values. So we know that this a from above is the initial amount. So the initial amount in our first year that we're talking about anyway, which was 2000, but we're just going to use is our first year, or actually at our starting point. So the initial amount was 2 million, which we're just using 2 for to represent millions. 1 plus annual growth percentage of 3.2, which we're going to put as, we change that to decimal form, so 0.032 to the x power. And so our function is f of x equals 2 times 1.032 to the x power. So that is the exponential growth function. And then in step B, it's saying use the function to determine Nevada's 2010 population to the nearest 100,000. Well, we can take our function and we can put in 10 for x, because this is 10 years after our starting point. So this was from 2000, we're looking at 2010. So x is going to equal 10. We have to be careful of that. We might think, oh, well, I'm going to put in 2010 up here. Well, that is going to be way off because we want just after 10 years. So we can put that in. So f of 10 is equal to 2 times 1.032 to the 10th power. We can put that in the calculator. You might want to do 1.032 to the 10th first and then multiply your answer by 2. But what we get here is 2.740, but they asked to the nearest 100,000. So we can go to 2.7 because, again, this is in millions. So this is millions and this is 100,000. So 2.7 million. That's how many would be around there in 2010. Next question says determine the average annual percent increase during the 1990s if Nevada's 1990 population was 1.2 million. Okay, well, this is kind of the same idea, but now we're looking at a different time frame. And so what we're looking at now is we want, we know, let me go back, we know in 2000 we had 2 million people, and in 1990 there was only 1.2 million people. And so our starting amount, which is, so this is not going to be the same function. It's not going to be function f because it's for a different time frame. We'll say g of x is going to equal a times 1 plus r to the x. And in this case, we're actually looking for what r is. Well, this is the amount after a certain amount of time. Well, we know in 2000, it got all the way up to 2 million. So our amount was 2 million. Our starting amount in 1990 was 1.2 million, so we'll just put 1.2. 1 plus r. R is what we're looking for to the x power. Now this is 10. So again, let me just go over this. Our reference point, or our starting point, is 1990. That's our year 0. We want to know how much it grew in the 90s. Well, to find that out, we figure out, well, what was it in 1990? And through the 90s, we know what it was after 1999, because in 2000 it was 2 million people. So we know our ending value, 2 million people after 10 years, and our initial amount was 1.2. Well, now we want to solve this. So what we can do is we're going to solve for r. We don't want to distribute because we have this 10 here, so we can divide both sides by 1.2. So we have this equation over here. These will cancel. The 1.2's will cancel. And we'll have 2 over 1.2 is equal to 1 plus r to the 10th. Well, we have the 10th here, so what we can do is take the 10th root of both sides. So it is important that you know how to use your calculator correctly. So we want to do 2 divided by 1.2, and you want to take the 10th root of that. A couple of things you can do. You can just take that number, and you can take it to the 1/10 power. If you do that, you get over here 2 over 1.2 to the 10th power root, the 10th root, sorry. You get 1.052 equals 1 plus r, and then you're going to have to subtract 1 from both sides, and you get r is equal to 5.2%. Well, we'll write this way, 0.052, and then we have to change that to a percentage. And so our the rate that Nevada's population grew in the 1990s was a 5.2% increase, which was even higher in the 2000s. Stemming from that same type of idea, after Nevada's silver rush, its population fell from 60,000 in 1880 to 47,000 in 1890. Use an exponential decay function to determine the average annual percent decrease in population during these years. This is set up the same way as the last one, except in this case we have a decay. So we'll start off with a function is equal to the initial amount, 1 plus r, which is the rate of increase or decrease to the x power, and that's our time in years. And so what we have here, after 10 years, so our ending amount, or our amount after 10 years was 47,000 equals, so I'm putting that in for my function. My initial amount was 60,000. 1 plus r, and r is what we're trying to solve for. We're trying to find the percent decrease to the x power. Well, our x is 10, and so maybe what I should have written here is we have a point 10 years, after 10 years, so in 1890, there's 47,000 people. And that's why I'm plugging 10 in for x and 47,000 in for the y value or the f of x value. And we would solve this the same way we did earlier. Looks like I'm running out of room here, so I'm just going to drop down here to this corner. We would divide both sides by 60,000, which if we cancel all of our thousands, we get 47 over 60 equals 1 plus r to the 10th. Take the 10th root of both sides as we did before. So similar solving here. So if we figure out this calculation, you'll have to use your calculator. You'll get 1 plus r is equal to the 10th root of 47 over 60 is 0.9758, so 0.976. Subtracting 1 from both sides gives us r is negative 0.024, which is a percentage, so we can say r is negative 2.4%. So this should be a negative here. Negative 2.4%, and a negative percentage means there was a decrease. Assuming the population continued to decrease at that rate, estimate Nevada's population in 1900 to the nearest 1,000. So we're going to use the same function. We now have r is negative 2.4%, so we can say f of x equals our original amount back in 1880 was 60,000. 1 minus 0.024, that was our percentage. And now we have to the 20th power, because this is 20 years later. Our starting time was 1800, and now we're talking about, 1880, now we're talking about 1900, so that's 20 years later. And you can calculate this. This is 60,000. 1 minus this was actually our 0.976 to the 20th power. So 0.976 to the 20th power times 60,000 gives us about 37,000. It said round to the nearest 1,000. So after calculating that, you get 37,000 would be the population if it continued like that. The last application we're going to look at, we're talking about here, is what's called a half-life. This is half-lives deal with exponential growth or decay, actually to decay. The half-life h of an element is the time that it takes for half of the radioactive isotope to decay into a stable isotope of another element. So there's a formula for this, radioactive decay, where you have your function in terms of t is a length of time, equals a, which again is the initial amount, just kind of like the last function we were looking at, equals half, which this is still kind of a percentage, 50% or half, of t over h. And h, that capital H, is the element's half-life. So example 5 here, the half-life of carbon-14 has been determined to be about 5,730 years. A piece of wood believed to be 4,000 years old now contains 19 grams of C14, the carbon-14. Predict the original amount of carbon-14. All right, the half-life of carbon-14 has been determined, so we just have this exact same thing written here. Sorry about that. Predict the original amount. Well, the original amount here is A. So what do we have here? Our function for this is, we're just taking it from above, radioactive decay. The half-life f of t equals the original amount times 1/2, and then in the exponent we have our time over the half-life for that known element. Well, we have 3 of the 4 pieces of information here. We have the amount after a certain time. It contains 19 grams, so this is 19. We're trying to find A because it says predict the original amount times 1/2 to the T over H. Well, the time here is 4,000 years, believed to be 4,000 years old, so 4,000 over the half-life, which is 5,730 years. And that's all supposed to be in the exponent. Sorry, it doesn't look that way. Well, here's just some calculating that you have to do. So on the left, we still have 19 equals, we can do 1/2 to the 4,000 over 5,730. So we have A times 0.61639, dividing both sides, let's put this in parentheses, dividing both sides by that 0.61639, 19 divided by that gives us A, so A ends up equaling about 30.8 grams. And then this next question says predict the amount of C14 to the nearest 1/10 of a gram in the wood 100 years from now. All right, so we found our original amount, so we can put that in, so our equation, we're going to take our equation from above, except now we have the original amount, so we have 30.8 grams times 1/2 and now we're going to take 100 over the half-life, which was 5,730. This is a straightforward calculation. You can do 1/2 to this power and then multiply it by 30.8, and you get 18.8 grams. And that's it for this lesson, some uses of exponential functions.